This is Atomic Radius, which is Chapter 5, Syllabus 14 through 15 by Riley Offit and Rory Cullenbach.
Okay, so first we're going to be talking about periodic trend. So the definition of periodic trend is properties of the elements that can be predicted from the arrangements of the periodic table. And they can be used to predict the elements' properties such as size and reactivity.
Next is the atomic radius. So atomic radius is the distance between the nucleus of an atom and its valence shell. The valence shell is drawn closer to the nucleus, making the atomic radius smaller as you go across the period. So farther on the left is bigger. And you can determine the atomic radius by doing half the distance between adjacent nuclei or bonded nuclei. Therefore, there's no defined edge of an atom because of the electron cloud, so you can't measure from the edge, which is shown in this diagram over here, that you are calculating it from the nucleus to the other nucleus, and then you divide that by 2.
Okay, so now we're going to be talking about period trends. So period trends are from left to right or horizontal on the periodic table, and the atomic radius decreases from the left to the right. The number of protons and valence electrons increases as you move to the right, but they are still in the same energy level. No further shielding, so there is a strong nuclear pull. The trend of smaller atoms across a period is caused by the increasing positive charge of the nucleus. And as electrons are added to the S&P sublevels in the main energy level group, they are gradually pulled more closer to the highly charged nucleus. The difference between radii and neighboring atoms in each period grows smaller. So, for example, potassium and calcium are in the same period, but calcium would have a smaller atomic radius than potassium because it is closer to the right.
Next, for group trends, as you go down, the atomic radius increases. So from the top all the way at period 1 all the way down to period 7, you are going to get bigger. And this is because the shells are increasing. So there are more energy levels causing more shielding and less nuclear pull. As electrons occupy sublevels in successively higher main energy levels farther from the nucleus, and in general, the atomic radii of the main group elements increases down the group.
Okay, and then here I made a little diagram to kind of show you. So imagine looking at a periodic table and looking at this. So the arrow is showing that the atomic radius is decreasing as you go to the right, but as you go down a group, it is increasing. So from top to bottom, and the arrows show that.
Okay, so here's an example. So what is the largest and smallest radius between magnesium, chlorine, or sodium? So here, magnesium is shown right here on the periodic table. Chlorine is over here, and sodium is first. So since sodium is in the first group, magnesium is in the second group, and chlorine is in the 17th group, which is farthest to the right. Chlorine is going to be the smallest since it's closest to the right, and the atomic radius gets smaller as you move to the right on the periodic table. So now you're going to be in between sodium and magnesium, but since magnesium is one more to the right, sodium is going to be the largest since it's all the way on the left. And they're all in the same period, so you don't have to worry about getting larger as you go down. Okay, one more example is the largest and smallest atomic radius between lithium, oxygen, carbon, and fluorine. So carbon is shown right here in the 14th group. Oxygen is shown here in the 16th group. Fluorine is shown in the 17th group, and lithium is shown in the first group. They are also all in the same period, which is the row. So since lithium is already the furthest on the left, you're going to know that that has the largest atomic radius. And then you're going to move to the right, which they will continuously get smaller, and you have your carbon, oxygen, and fluorine. So carbon and oxygen are not as far to the right as fluorine, and fluorine's the farthest to the right out of all of them, so it's going to have the smallest atomic radius.
And that is it for atomic radius.